So in this video, I'm going to use double integrals to find the center of gravity of this plate that's comprised of a lower function of y equals x squared and an upper function of y equals 9. Clearly, these curves intersect at 3 and -3 on the x-axis. Okay, so the formula for the center of gravity for the x, there's an x-coordinate and a y-coordinate. The x-coordinate is given by this double integral of x dy dx from a lower function of x squared to an upper function of 9 and a lower number of -3 and an upper number of 3. Divided by the double integral of 1, I'll put that there for emphasis, dy dx, between the same limits, x squared and 9 and -3 and 3. Okay, so that's the x-coordinate. The y-coordinate is similarly defined. Okay, go down here. So y bar is equal to the fraction, the double integral of y dy dx from x squared to 9 and -3 to 3 over the same thing, same exact integral, double integral of 1 dy dx from x squared to 9 and then from -3 to 3. Okay? Well, in this problem, we're lucky because the computations are cut in half due to the fact that the plate that we're talking about is symmetric about the y-axis. All right, so the x-coordinate is going to be 0 naturally, right? If we want to put our finger someplace to balance this object, of course, it's going to have to be on the y-axis because there's equal mass on the left and right. So the x-bar integrals are unnecessary. Of course, if we carried them out, we would find that x-bar is equal to 0, but we can just look at the picture and know that. So this one's gone. So all we have to worry about is this integral. Now, let's try to get some intuition about the problem, all right? For example, let me draw the halfway line. So if we have 1, 2, 3, 4, 5, right? The halfway line up to 9 is here, okay? Well, that's going to be no good, right? Because as a point, right, at 4.5, because we're going to have more mass on top than we would on the bottom, right? So the thing is going to tilt over if we try to put our finger at 4.5. So the place where we're going to be able to balance this plate is going to have to occur, above 4.5 someplace, right? Because we're going to want to put a little more mass on this side, due to the fact that we have a lot more up here. So we're expecting a number that's bigger than 4.5. All right, so let's see what it turns out to be. So to do these double integrals, we do them in stages, right? So we have the innermost integral, right here. So we'll worry about the numerator first, and then we'll take care of the denominator. So to do the numerator, like I said, we draw a box around the innermost integral. We'll do that, and then we'll do the resulting x integral afterwards. All right, so the integral on the inside is x squared to 9, okay, of y dy. Okay, well, that's going to be equal to 1/2 y squared, evaluated between x squared and 9. And then using the fundamental theorem, we'll have 9 squared, which is 81. So we have 81 over 2 minus x squared squared over 2. So that's going to be 1/2 x to the 4th, right? If you square x squared, you get x to the 4th. Sound good? Good. Good. So we'll replace the inner integral with this function of x, and then we'll do the resulting x integral. Right? So in here, we have 81 over 2 minus 1/2 x to the 4th. So to finish the numerator, let's do the outside integral now, right? So we have the integral from -3 to 3 of 81 over 2 minus 1/2 x to the 4th. Okay? All right, so what do we get? We get 81 over 2x minus 1/10 x to the fifth. Okay, we get 1/10 x to the fifth because we add 1 to the exponent, giving us 5, and divide by 5, then times 2. 2 times 5 is 10. And this is going to be evaluated between -3 and 3. All right, so I'll write equals because we're going to have a numerator here soon. So if I plug in a 3, I get 81 times 3. That's 243 over 2 minus 1/10, okay, times what? 1/10 times 3 to the fifth. Well, 3 to the fifth is also 243 because 3 to the fourth is 81 times 3 is 243. Perfect. Okay, minus all this evaluated at -3. Well, if we plug in a -3, we get 81 times -3. That's -243 over 2. Then we have minus -3 to the fifth. So that's -243. But then negative is plus. We get plus 243 over 10. Okay? Fantastic. So what does all that equal? Well, 243 over 2 minus is plus 243 over 2. So it's half of 243 over 2 plus another half of 243. So we get 243, right? Half of 243 plus another half of 243 is 243. For the second term, we have negative 243 over 10 minus another 243 over 10. So that's negative 2 groups of 243 over 10. We can cancel the 2 and we can write 5 in the denominator. So we have 243 over 5. Fantastic. So let's do more with this numerator, right? I can factor out a 243 and then I have 1 minus a fifth. But 1 minus a fifth is 4/5. So I get 243, okay, times 4 all over 5. And that's going to be the number in my numerator here, right? So I get 243 times 4 over 5. 243 times 4 over 5. I'm going to leave it this way because I'm going to hope I get some canceling later. Okay, well, let's deal with the two integrals we have in the denominator, all right? I'll erase this because it's a tape, and you can stop it if you want to look at it. All right, so for the innermost integral, right, and that's the way we do it, right? We do the inner integral and we do the outer integral. For the inner integral, we have the integral from x squared to 9 of 1 dy, right? Well, the integral of 1 with respect to y is just y, and that's evaluated between x squared and 9. So if we plug in a 9, we get 9. Plug in an x squared, we have x squared. So the fundamental theorem gives us 9 minus x squared. So we have 9 minus x squared inside this integral here. Okay? So let's do the outer integral. Well, the outer integral is the integral from -3 to 3, okay, of just what we obtained, 9 minus x squared dx. Well, doing the x integral now, we have 9x minus 1/3 x cubed, evaluated between -3 and 3. Let's see what that does. So if we plug in a 3, we get 9 times 3, and that's 27. Minus 27 over 3 is 9. Minus, we plug in the negative, so we have 9 times -3, that's -27, right? And then -3 plugged in for x cubed is -27. Negative is +27 over 3, that's +9. Okay, sorry to be writing all the way over to the edge, but we'll... I'll say it so you can compute it. I'll rewrite it. 27 minus 9 minus -27 plus 9. Okay, so if we combine the 27s, we have 27 plus 27, that's 54. right? And then negative 9 minus 9 is minus 18. So all this gives us 36. So in the denominator, we have 36. So let's see what all this equals, shall we? So I have 243 times 4 over 5. So I'll put that 5 in the denominator with the 36, right? And this is going to be our y bar. All right, well, 243 is 3 to the 5th. Okay, that's where we got it from, times 4. Downstairs, what do we have? We have 5 times 9 times 4. 5 times 9, 9 is 3 squared, times 4. So we have the 4's cancel. 3 squared cancels with 3 to the 5th to give us 3/3. 3 to the 3rd, and we have 27. 3 cubed is 27, divided by 5, which is equal to 5 and 2/5, which is 5.4. Well, this fits with our intuition, doesn't it? Because our intuition said that the point where we can balance this plate has to be a little bit above the halfway line. And 5.4 is certainly a little bit above the halfway line. So 5.4 is right about here. Okay. So if we have an x bar of 0, right? X bar of 0, and then a y bar of 5.4, okay? This looks like a decent point to put your hand to balance that metal plate. So this is a nice use of double integrals.